now I want you to use MATLAB to obtain certain results. So I think one of the questions says, you know, discretize this matrix, okay? So I want you to go find the equations that are required to discretize, type them out in MATLAB, publish the results, print it out, that's what you turn in. I think everything except for problem number 5 is going to be done that way. So I think there's only 5 problems. 1 through 4 are all going to be MATLAB based. So that is going to be due April 3rd. And that's weird because we only have one class between now and April 3rd because of Easter. So complain now. I can push it back. We can make it due April 5th, but I still have another homework to assign and then a project at the end. And so as of now, that project will be due, you know, during finals week. So I'm kind of pushing up the due date a little bit. I don't think it should be that big of a deal other than, I don't know, potentially cramping the Easter holiday. Does anybody have any issues with that? Like I said, we could push it back, but then the minute you turn in your homework, I wanted to give you another one. We'll see how it goes. Go ahead and chew on it, work on it this week, next week, and we can discuss that on Tuesday. All right, so long time ago, we were talking about equivalent systems. And the idea is that I can use these transformations for my ABCD matrices in a state space representation of an LTI system. I can transform that to create 4 different matrices that represent the exact same system. They all have the same input and output characteristics. And there's reasons that we can, or there are reasons why we would want to utilize these transformations to simplify the state space representation of an LTI system. Okay, so this is a state space representation of an LTI system. So what we're going to do is we're going to do the same tricks that we've done before. We're going to try to diagonalize the square matrix. That A matrix, we're going to make it a diagonal. So what do we have to do? We have to find eigenvalues, we have to find corresponding eigenvectors, and then we diagonalize. Okay? So how do we go about doing this? First, I want to split this out into different equations. So this would be negative 2 x 2. Okay, so just from those matrix representation, I can find 3 independent equations that relate to change in state, the current states, and output to current states. So now, I want to take that matrix A, and I'm going to look for its eigenvalues. Okay, so how do we do that? We take the determinant of lambda I minus A, and we set it equal to 0. Okay, so if I do that, I get lambda 2, negative 1, negative 1 plus 3. Then take the determinant. Multiply each of the diagonals, add them together, actually subtract one from the other. Looks like my eigenvalues are -1 and -2. Okay, so now that I've got my eigenvalues, I can use those eigenvalues to determine eigenvectors. Right, I do that by solving that equation. A minus lambda I times x equals 0, and we're going to solve for x. Okay, x will be my eigenvector. So put in -1 for lambda, and so A is 0 minus -1 is 1. -3 minus -1 is -2. And I only get one equation out of that because they're both the exact same. Okay? So I've got 2 unknowns, 1 equation, which means I have 1 degree of freedom. So I'm just going to choose something. I can choose anything. Anything's going to work. But let's make it easy. We'll say that x2 is equal to 2, and x1 is going to be equal to, sorry, x2 is equal to 1, and x1 is equal to 2. Okay, I can do, so that's one of my eigenvectors. Find my second eigenvector, we do the exact same equation. We put a different eigenvalue in there. So I get 0 minus -2. And now I've got -3 minus -2. Is that right? That doesn't seem right to me at all. -2 I messed up. Hold on. And is equal to negative.
Then we have -2 in the top right.
Thank you. So then -3 minus -2 is -1. Okay, again, we have only one equation, right? These 2 equations are the exact same equation. All right, if we simplify them out, they say that x1 is equal to x2, so I've got a degree of freedom. I can choose whatever I want. I'm just going to say that have two eigenvectors. What I'm going to do now is create a matrix by lining up each of my eigenvectors by a column. Okay? And then traditionally what we would say is we would diagonalize this matrix by that. Q inverse times A times Q. But if you look, our equivalence transformation says it has to be P, A, P inverse. So this is actually going to be P inverse. Okay, so my eigenvectors are P inverse. I can find P, and then I can diagonalize my system. I'll show you here in a second what that diagonalizes to. I guess I just will do that. Okay, so this is our original A, B, C, and D matrices, and then I'm just going to plot a step response. Okay, so my input U is just a bunch of ones. That's going to be my step input. I'll run it through a simulation. I'll find the output, and then I'm going to do what we just found. Okay, so our inverse P, which is conveniently hidden behind the board, was exactly this, right? It was a column vector of 2 and 1, and another column vector of 1 and 1. And again, we had choice in this. We can make this anything we wanted. Maybe I'll go nuts out here. Call this 10 and 10. Because that should be okay, right? We're still following the rules. So then we'll diagonalize that A matrix and do an equivalence transform just like this. Run the exact same simulation for a step response. And then plot both the results. What's going on here now? Then I do a scaling for some reason. Okay, so we did a little magnitude scaling here. Don't really know why we're doing that, but we can go ahead and that. So here's my original A, B, C, and D matrices. Hopefully they line up with exactly what the example was. And this is what our states look like, and then the blue line is what the output looks like. If I then diagonalize, you can see that I've got, now A is diagonalized, and I've got different A, B, C, and D matrices, but A has been the one that we really want to look at, and you can see that our outputs are the same. So comparing 1 and 2, they're the same. And then my magnitude scaling is going to be all messed up. Actually, it's not so bad, because I changed my diagonalization, so the states are going to be all different. So let me get rid of this. We'll run it one more time. So there's the first one, there's the second one. Then I noticed, remember if we're thinking of an op-amp design, the output of those integrating op-amps were the states, right? So I gotta be worried about the states because there are actual voltages on those op-amps. And you can see that I've got some voltages on states that are way out of bounds from the other ones. So this one could be reduced by maybe like a quarter, and that one could be reduced by maybe like a half. So I'm gonna go through a third or second equivalence transform where I recognize that x1 is 4 times too big and x2 is 2 times too big. And just recognizing that my equivalence transform becomes really simple. x1 is 4 times too big and x2 is 2 times too big, so I just scale them accordingly. So that's my my P matrix, and it's just a diagonal matrix. And I do the exact same thing again. We do that again. You'll see, hopefully, that of course my input and output relationships are solid, but also that my states now are all within the same range, and my output, because the output's also a voltage in the circuit. Does that make sense? So if you have a state that's 100 times another state, it's not going to work in a physical circuit. So just got to keep that in mind. We start bringing in the power supplies and stuff. Any thoughts on equivalence transforms? All right. Hopefully we've gone over it now enough that it at least makes a little bit of sense. Okay. All right, we all know that we can get an output by multiplying the transfer function by an input function in the Laplace domain. We can also find a relationship to the Laplace representation of an LTI system and the state space representation of an LTI system. By taking the Laplace transform to each of those parts, the only one that's any sort of anything complicated is that change in x, right? The derivative of x, if I take the Laplace domain, it's going to be s times x. Okay, and so I can use these two equations, substitute one in for the other, and find a representation of the transfer function of my LTI system. So the first thing I need to do is solve for my state, x of s. I can do that. putting everything on the left-hand side. Okay, if I isolate x, and then I can multiply both sides by that inverse. I get that. And now all I have to do is take the definition of x, substitute it in here. Then I get my output in terms of my input. Of course, if I take my output over input is what? Output over input is your transfer function. So this is y, this is u, my output over my input. I'll just say okay, so we got a simple transformation from state space to transfer function. Okay, somebody over in the math department figured out that the inverse of A can be expressed by the adjoint of A over the